So recall the magnetic field system is a conservative system. Which means a lossless system. And this cannot be assumed unless we ignored the hysteresis and the eddy current losses. And simply, for example, the eddy current losses can be reduced by using a laminated core. And hysteresis losses can be also reduced by the material selection. To select a material with high permeability, this can also reduce the hysteresis losses. Now, who know the meaning of the conservative system? Or let's say examples of the conservative system. Do you know the conservative system is what?
دكتور بتكون الفورس يعني اللي done بتكون يعني independent of خلينا نحكي losses path like that.
So simply this means that in this system the work done by the force is independent of the path. Yeah. So simply is a system in which the work done by the force or the work done by the system is independent of the path is taking. The second one, the work done is equal to the difference between the final and the initial values of the energy function. The work done is equal to the difference between the final and the initial values of the energy function And the last one, this is a completely reversible. So for example,
electric field دكتور.
the electrical field. Also, let's assume that I'm neglecting the losses, and let's assume that I'm having a ball, and I need to move the ball from position A to position B. And here I'm neglecting the resistance of the drag force, let's say, and the friction. And let's assume that this is a lossless system. Now, if I move the ball from A to B, either using this path or using this path or using this path, in the end of the day, the work done by the force is independent of the path, yes or no? Here, the potential energy are the same, whatever I'm discussing, whatever path I'm taking. Yes, the potential energy here depends on the height and the mass of this, let's say, ball or object, and it's independent regarding the path that I'm taking. And it's depend on what? It's equal to the difference between the initial position and the final position, correct? Yeah. So this is actually is example for regarding the conservative system, such as gravitational potential energy, also electrical fields. What about non-conservative system? Simply, it's very simple. Any system contains losses. It's what?
Heat matter.
So any system consists of losses such as frictional force, air drag, and so on, is a non-conservative system. So now, under our assumption that I'm neglecting the hysteresis and the eddy current, and this also can be done by material selection, I can eliminate or reduce, or not say eliminate, mitigate the hysteresis losses. And by using laminated core, I can suppress or reduce the eddy current losses. So in this case, I can assume that the magnetic field is a conservative system, which is a lossless system, which means that the work done is independent of the actual trajectory of the state. Yeah. So if I'm having here, for example, a current trajectory, let's assume this is the time and this is the current, and I need to find the work done at this point, let's assume at T1. So the work done by the current at T1 is independent regarding the path. So if I'm taking this path, or if I'm taking this path, or if I'm taking, let's say, this path, in the end of the day, here, at this point, so let's assume that at this point, the energy are the same. So if this is the case, I can do the integration using two steps. So now let's try to find the integration. So I will start with V1. V1 is equal R1 I1 plus d by dt of lambda 1, and lambda 1 can be written as L1 I1 plus the mutual inductance multiplied by the second current, which is the I2. I'm assuming two coils or one, okay, two coils, coil number 1 and coil number 2. So this is the first equation, the voltage equation for the first coil. The second coil voltage equation, R2 I2 plus d by dt of L2 I2 plus M I1. Yeah. So now I need to calculate the field energy for the multi-excitation system. And I don't need to carry the losses with me, so I will assume directly now R1 equal R2 equal to 0, because even if I have it, I would say that I1 square R1 is the ohmic losses and I2 square R2 is the ohmic losses. So I will assume from now on that R1 equal R2 equal to 0. I only need to calculate the mechanical power plus the rate of the change of the field energy. So if we do so, we will have that the P mechanical plus d omega f by dt will equal to I1 d by dt of L1 I1 plus M I2, the first one, plus I2 d by dt L2 I2 plus M I1. Now, if I can calculate omega f, I can find the mechanical power. So I need to calculate omega f, which will equal the integration of V1 I1 plus V2 I2 dt. And because we assume that the energy is independent, how I1 and I2 are reaching their final state, I can do the integration using two-stage. So here we can write, recall, the energy is independent how I1 and I2 reach their final state. So simply this means that we can do the integration can be done by using two stages. Stage number 1, I will assume that I2 equal to 0, and I will evaluate the integration as I1 is changing from 0 to its final value. Then I will recalculate the integration or re-evaluate the integration under stage number 2 when I1 is reaching its final value while I2 is changing from 0 to its final value. Of course, there is no meaning of I1 or I2. I1 can be I2 or I2 can be I1 because I1 and 2 is labeled, you know that. So this means that I can also do the integration using the following stages. I will reverse the stage number 1. I will say that I1 equals 0. And I will evaluate the integration. I will evaluate the integration as I2 is changing from 0 to its final value. Then stage number 2, I will assume that I2 is reaching its final value, and I will evaluate the integration as I1 is changing from 0 to its final value. So if I use the first method or the second method, I should get the same result. So let's try to evaluate the integration. I will rewrite here the integration. So I1 d by dt L1 I1 plus m I2 dt plus I2 d by dt L2 I2 plus m I1 dt. And I will start with stage number 1. So if I evaluate using stage number 1, in stage number 1, I will assume that I2 equal to what?
0.
I2 equal to 0. So if I2 equal to 0, this means that this term is equal to 0, correct?
Yes.
Yeah. And this term is equal to 0. Yes?
Yes.
So I will end up with only the first term due to the stage number 1, which is I1 d by dt of L1 I1 dt. And this one is due to stage number 1. Where we assume that I2 is equal to 0, and I will evaluate the integration as I1 is changing from 0 or from the initial value to its final value. Then, now I need to do the integration second time under stage number 2, which means that I'm assuming now I1 is reaching its final value. So if I1 is reaching its final value, any d by dt of the final value is equal to 0, correct? So this term, if I differentiate the current, it equals 0. Why? Because I1 now is reaching its final value. It's constant now. So I will end up with what? I1 d by dt m I2 dt plus this one is equal to 0 plus the integration of I2 d by dt of L2 I2 dt. And this term here is due to stage number 2, which means that now I1 is equal I1 capital, and this one is constant. And I'm evaluating as I2 is changing from 0 to its final value. Now, if we do the math, we can find now the field energy, omega F, is equal. The first one, 1 over 2, L1 I1 square. This one, if I need to evaluate, this will equal to M I1 I2. And if I evaluate the last term here, this will equal 1 over 2 L2 I2 square. Yeah. Good. Now, if this is the field energy, I need to calculate the rate of the change in the field energy in order to extract the mechanical power. Now, the rate of the change of the field energy is d omega f by dt. So this will be d by dt of the field energy, and we have here the field energy. 1 over 2 L1 I1 square plus m I1 I2 plus 1 over 2 L2 I2 square. And let's assume that I'm discussing a cylindrical rotor. I'm discussing what? A cylindrical rotor. So let's assume that if we have a cylindrical rotor, then L1 and L2 are constant or time varying.
Constant.
Why?
Uniform air gap.
Yeah, because the gap is uniform, so are constant independent of theta. Now, what about the mutual inductance? The mutual inductance will change with respect to the rotor position. Why? I think we discussed before, huh? If I redefine the mutual inductance actually is how much of the flux generated in one coil will link the second coil. And if I still remember, we discussed somewhere here maybe. Where is it? We discussed somewhere. I think we discussed it. Yeah, this one. Yeah. So simply at this position, the mutual inductance has certain value. At this position, the mutual inductance is the maximum. At this position, the mutual inductance is the minimum. So simply it can be seen as the mutual inductance depend on the cosine of the rotor angle. So if this is the case, if I need to evaluate this one under the cylindrical rotor, which means that L1 and L2 are constant and only M is the time varying. So who can help me to evaluate the rate of the change of the field energy? So if I evaluate this one, the first term, this is equal to what?
LS.
Here I'm using one and two. Huh? So L1 I1 d I1 by dt plus here
L2 I2 di2 by dt
L2 I2 di2 by dt plus what about this one?
I1 بالنسبة ل I1 ل I2 M I1 di2 by dt
So M I1 di2 by dt
plus M I2 di1 by dt
di2 by dt plus
plus
I1,
I1
I2.
I2 dm by dt.
Yeah,
Mutual
because M1 is a function of theta, so I should differentiate. So this will be I1, I2, partial M or dm by d theta. dm by d, okay, or dm by dt. Yeah. So until here, we have the rate of the change. So if I'm having the rate of the change, I can go back in the previous slide, I think here. Yeah, this one, if I subtract from it d omega f by dt, I will get what? Bm, the mechanical power. So if we have the P mechanical plus d omega f by dt, and this was equal to I1 d by dt of L1 I1 plus m I2 plus I2 d by dt L2 I2 plus m I1. So this will equal to I1 L1 di1 by dt plus I1 I2 dm by dt plus I1 I1 m di2 by dt, this is the first one, plus the second term here. This will equal to I2 L2 di2 by dt plus I1 I2 dm by dt, and finally I'm having I2m di1 by dt. So calculating now the mechanical power is very simple. P mechanical will equal this term minus d omega f by dt, and if we do the math collecting the terms, this will equal to I1 I2 dm by dt, and m, because m is a function of theta, so the P mechanical now can be written as I1 I2 partial m with respect to partial theta d theta by dt, and this will be the torque. Remember that the mechanical power is equal to the torque multiplied by the angular velocity. Good. Yeah. So simply, if we can represent the mutual inductance M as certain inductance, let's say M small cosine theta r. So when the two coils are elegant to each other, this will be the maximum coupling. Here theta r is equal to 0, and or let's say here M max. If theta r equal to 0, then M will equal to M max. And if theta r is equal to 90 degree, then M is equal to 0. And if I evaluate the torque will equal to, if I calculate it, I1, I2, partial by partial theta, and instead of M, I will put M max cosine theta R. Now, if I evaluate, this will equal minus I1, I2, M max sine theta R. If we plot the torque with respect to the rotor angle, this would be minus sign, scaled minus sign. So this is the theta R, and this is the electromechanical torque. If I plot it, it will be scaled sign. Let something like this here. Something like this, huh? Yes. So this is the 0, this is the pi over 2, the minus pi over 2, and this is the pi, and this is the minus pi. Now, for this plot, which is the torque versus the rotor angle, let's define positive torque or negative torque. What's the meaning of the positive torque and what's the meaning of the negative torque? Now, the positive torque acts in direction of increasing the rotor angle. So here we can write that positive torque acts to increase the rotor angle in the same sense. The positive force, so the positive force acts to increase the displacement, rotor displacement. Understood? So now let's see. If the torque is changing, let us assume a positive torque is changing. Now I'm here at this, let's assume that this is my initial position. This is my initial condition, let's assume. And I'm making change in the torque. So I will impose a positive torque. So the positive torque will act to increase the rotor angle. So I will go to this side. I will go to this side or to this side, according to our definition of the positive torque here.
Left side.
So similarly here, I'm here. Yes?
No, reverse direction.
Now this is what? Let's assume that I'm change the torque. So the torque is here. This is what we call what? The torque speed, the torque angle plot. So for any reason, let's assume that any disturbance happened to the system. I am here. I am here. Let's assume that for any reason, a disturbance, the rotor is changing. Now, here, the torque is positive or negative here?
Negative.
Positive.
No,
Negative.
negative. If the torque is negative, then the negative torque act to decrease the rotor angle, correct? Because the positive torque act to increase. So simply this means that this point will return back to the zero, yes or no?
Yes.
What about if we have the opposite scenario? For any reason, I'm here. For any reason, I'm here. Now, at this point, the torque is positive or negative?
Positive.
So the positive torque acts to increase the rotor angle. So I will return to the same point, at the zero, correct? So simply this point is called the stable equilibrium point. Now, what about if I'm here at this point? You know that at this point, the torque equal to what? Zero. At this point, the torque equal to what? Zero. At this point, the torque equal to what? Zero, correct? So let's assume I am at this point. And now there's a disturbance and disturbance. The disturbance can push this point either to the left or to the right, correct? Let's assume I'm here. Let's assume that for any reason I'm here. Now, here the torque is positive or negative?
Positive.
So according to the definition of the positive torque act, increasing the rotor angle, correct? Now let's assume the opposite scenario. For any reason, a disturbance happened. I am in this point now. At this point, the torque is positive or negative?
Negative.
And the definition of the negative torque is what? The negative torque act to decrease the rotor angle. Huh? So simply, I will go in the opposite direction, correct? So simply this unstable point. This is unstable point. And this is can be seen as the definition of the stable equilibrium point and the unstable point. So simply this means that the machine will never rotate here. Huh? I'm having pulsating torque. Yeah. So if I need the machine to rotate, what I should do? I need to add more excitation in both the stator and the rotor to make the machine rotating. So simply a single coil on the stator and a single coil in the rotor can generate a pulsating torque, but this pulsating torque is not sufficient for the machine to rotate if I'm having a cylindrical rotor. So for this, we need more excitation in both stator and the rotor to make the machine rotating. So yes.
ترى أنا مش فاهمة ليش unstable point.
Just a minute. Let me finish writing this sentence and I will return back. So in both stator and rotor to make the machine rotating. Okay. Okay, so let's return back to this graph. And for that, I will replot it here. Add page. Now, according to our derivation of the torque, it was scaled minus sign, correct?
Yes.
Yeah. So simply the torque has its value according to the theta, this plot of theta r versus the torque. Yeah. Now, because the torque is zero at certain position, so for example, the torque here is zero. The torque at this position is zero, yes or no?
Yes.
The torque here is zero.
Zero.
The torque here is zero. The torque here is 0. The torque here is 0. Yes or no?
0.
Okay. So simply this means that the rotor will, let's say, stop at certain position. Yes, because the torque is 0. Yeah. So let's assume I am at the first point number 1. This point. Now the status of the machine at this point. For any reason, there's external force. I'm pushing the machine. I'm rotating the machine by hand. So simply this means that theta r will change. Yes or no?
Yes.
I'm doing disturbance. You know the disturbance?
Yes.
So this disturbance can cause either the rotor angle to increase or the rotor angle to decrease. Yes, according to its direction. Yes?
Yes.
But because it's disturbance, I will discuss the two scenarios, either increasing the angle or decreasing the angle. Yes? So let's assume for any reason I'm here, which means that the disturbance cause the rotor angle to increase. Yeah?
Yes, and torque negative.
So in this case, the torque will be what? Negative.
Negative.
The torque will be generated as a negative torque. The negative torque, as by definition, is what? A torque that acts in the direction to decrease the angle. So simply this means that the angle will decrease until it settles down in the same point. Yeah?
Yes.
What about if the opposite scenario happened? Now the torque is what? Is positive. The definition of the positive torque is what? Acting to increasing the angle. So I will go increasing the angle until reaching the 0 point, which is the steady state point, correct?
Yes.
So simply this means that this point is a stable point.
Yes.
Yeah, which means that if I am here, whatever disturbance I'm having, maybe I will oscillate, but I will return back to what? To the same point. Yeah.
يعني
So
دكتور حوالين هاي النقطة بيكون unstable بس عندها بالضبط stable.
Now there is something called operating point.
Operating point.
Yeah, the operating point here is simply this is an operating point. This which means that the machine can stay there, but simply the machine will never stay here. Why? Because if I am at point number 2, a torque will generate. If the torque is generating, I am in the transient until I'm reaching the steady state. Yes?
Yes.
So this is what we call the equilibrium point or the steady state point. Yeah? A point when the system is still down or the derivative d by dt will go to 0. So this is a stable point. What about this point? Now in this point, let's also discuss the same.
طيب دكتور نقطة 1 نفس النقاط الأطراف كمان نفس الشيء بتكون.
Actually, yeah, because this one is 2 pi, yeah? You know that. It's cylindrical.
Yes.
So if I'm starting here as this is my reference, so this will be what? 2 pi, yeah?
Yes.
Yeah. Yes, of course. This one and this one is the same, huh? This is the 0. This is the pi over 2. This is the pi. This is the minus pi. And this is the minus pi over 2. So I need only to discuss this, let's say, rotor span. Yeah? Now, what about this one? If I am here at this point, point number 3 or A, whatever, for any reason, if I'm here, can I stay here? No. Why? Because there's a torque. If there's a torque, now I should move. If this torque is positive, I will go increasing theta. If this torque is negative, I will reduce theta. Now this torque, positive or negative?
Negative.
Negative. So I will do what? Decrease theta. So decreasing theta until I'm reaching where? This point.
Stable point.
The stable point. So this is unstable point. Yeah. The same thing.
Yes.
What about from here? The torque is what now? Positive.
Positive.
So the same thing. I will increase. It will act. Positive torque act in direction of increasing the angle until I'm reaching what? The 0 point. This point and this point are the same. Huh? Yes. 0 pi. This will be what? The 2 pi. Yes. So this is the definition of the positive torque, negative torque, the stable point, and the unstable point. Yeah. Another thing,
Yes.
this torque, the average value of this torque is 0. So this is called pulsating torque. Yeah. So simply, this means that if I need to design a machine in order to rotate, I need to add more excitation. It's not enough to have one coil in the stator and one coil in the rotor in order to do the excitation. Yeah. Good.
Yes.
Good. So now I need to find a way in order to calculate the, let's say, the torque or the force directly from the field energy. I don't need to go in the same thing to find the instantaneous power, then to find the to swing out, let's say, the losses, then to find the field energy, subtract the rate of the change of the field energy from the remaining part. I need to find the formula. Can I link the force or the torque to the field energy or no? So let's try to answer this question. And for that, let's discuss the magnetic circuit. In general, until now, we are assuming a linear magnetic circuit in which the relation between I and lambda can be written as lambda is equal L I. So this is I lambda curve, let's say. And here, let's assume it's linear. So if linear, this means that this one, let's assume it. And here lambda is equal L I. Now, if we remember, the field energy was equal to what? Omega F was equal the integration of I d lambda. I d lambda. So if this is the curve and I need to find the integration of I d lambda, recall that the integration is actually the area under the curve. So simply I'm discussing this area, correct? Yeah. This actually is the integration of I d lambda at certain point. Huh? Let's assume I'm discussing a certain point here. Okay. Now, this area is called the field energy. Or what we call it, WF. Now, the same thing, this one is the complement of the area. Yeah. So let's call this area the Coenergy. So this area, we will call it the Coenergy. And if I need to find the Coenergy omega C, if I need to find the area here under the curve, this one, this is equal to what? The integration of what?
Same, يعني omega F.
This will equal lambda di. Here the variable is I and the curve represent lambda, correct? Here the opposite.
Yeah, yeah.
Here the curve is the current and I'm changing what? Lambda. So omega F is the integration of I d lambda and omega C is the integration of lambda di. Huh? Yes?
Got it.
Now, if I'm having nonlinear magnetic circuits, so let's assume now I'm having nonlinear magnetic circuit. The same thing, this is I, lambda, and let's assume I'm having nonlinear saturation. So I will put here some saturation. And let's assume that I'm discussing the Fillmore point. Now the same thing, if I need to find this area, I will evaluate what? Omega f, yeah? Yes, the same thing, this area is omega f, which equal to what? The integration of I d lambda. And this area is what? Is also the Coenergy, which if I need to evaluate is lambda di. Now here, for linear magnetic circuit, omega f is equal omega c, yes or no?
Yes.
Here,
Yes.
No.
here in general, omega f not equal to omega c, yes? But omega f here plus omega c is equal to what? If I add this area to this area, then this equal to what?
Area.
I lambda.
I lambda.
And the same thing here. Yeah, if I add omega f plus omega c, it's still applicable. It is I lambda, correct? Yeah. So this means that the linear magnetic circuit has advantage. If I found the field energy, I found what? The Coenergy. Yes, without any calculation. Without any calculation, if I found the field energy, I will find the Coenergy. But this is not applicable for what? For the nonlinear magnetic circuit. So this is nonlinear magnetic circuit.
دكتور عم بالحالة الثانية اللمدة ما بتساوي اي في ال.
Who said that?
non-linear.
And what I did right there. This area. Do you see this area, the dash box? Equal to this area plus this area, yes or no?
No.
كيف no? If you have, let's assume that this is your box. This area plus this area is equal the area of this box.
Yes.
If I change this one to be something like this, this area, yeah, so omega f plus omega c is equal I lambda, whatever I'm having. But what's the difference between the two? Omega f is equal to omega c in the linear magnetic circuit, but in the nonlinear magnetic circuit, omega f in general not equal omega c. Huh? So this is linear. Yes. Yeah. Okay. Now, here I will discuss for linear motion, and it will be applicable also for the rotational system, which means that I will calculate the force. I will calculate the force. Now, if you remember, d omega f by dt was equal vi minus the p mechanical. And if I remove the ohmic losses, when I'm assuming that R go to 0, because I don't need to carry the ohmic losses with me, then I can say d omega f by dt is equal I d lambda by dt minus the mechanical power, and the mechanical power for the linear motion is equal the force multiplied by the velocity. Yeah, correct. So simply this can be written as d omega f is equal I d lambda minus f dx. Yes, until here nothing new, huh? So let's replot the I lambda curve. This is I lambda curve, and let's assume that for certain displacement I am here at x1. Now if the gap is changing, this curve will change or will be constant?
will it change لأنه بيأثر على الفلكس؟
Yeah, will change because the reluctance will change actually, and you know that the slope of this curve is actually the reluctance. So if the reluctance changing due to the gap changing, so simply maybe I will be here somewhere here, huh? So I will be somewhere here. Let's assume that I'm here, huh? So simply this means that each curve is valid for some value of x. So each curve is valid at certain position or displacement x. So someone will say this means that omega f, the field energy actually, is a function of what? Of the flux linkage and the displacement. Correct? If we recall, omega f was equal to what? The integration of what? Omega f. Do you remember it? I d lambda. So here the variable is what? Is d lambda, because if I change d lambda, the area will change. And if I change the position, then the curve will change. So simply this means that the field energy is a function of what? Of lambda and x. Yeah, so this means that the field energy is function of lambda and x. Correct? Yeah. So that's great. So we know that omega f is a function of lambda and x. Now I need to evaluate d omega by dt. D omega f by dt. How I can do that if f is a function of lambda and x? How I can? Chain rule. Can you help me with that?
d omega f by dx times dx by dt plus d omega f by d lambda times d lambda by dt.
Okay, so the d omega f by partial omega f by partial x.
Partial x by partial t.
When lambda is constant, correct? This is the condition of the chain rule, huh? Can I do the partial derivative without assuming the other variable is constant? I cannot. Yes?
Yes.
Dx plus. The second one is what?
Partial omega f by partial lambda.
By partial lambda, assuming what? X is constant. This is a mathematical requirement, huh? And this is what? D lambda. Yes? Yeah? Now, do you remember d omega f, I was write it as what? D before. Let's change the color here. D omega f, if I recall the previous one. Yeah, this one. I will take it from here. So let's take it, huh? I d lambda minus f dx. So this will equal I d lambda minus f dx, correct? Yeah?
Yes.
And now let's compare if this one, yeah, if this one and this one are the same. So here I can say that if I compare this one to this one, yeah. Now what we can see, okay. Now let's see. This is the dx and this is the d lambda, correct? This is the dx and this is dx and this is the d lambda. So if I compare, I will equal to what?
Partial omega f by partial lambda.
When x is constant. And the force will equal to what? Huh? So if I compare, then I will equal partial omega f by partial lambda when x equal to constant. And the most important thing that I'm seeking is the force. The force is equal minus partial omega f by partial x when lambda is equal to constant. Yes. Now the same thing if I need to calculate the torque. The torque will equal to what? Minus partial omega f by partial theta when lambda is constant. Correct? Yeah. If I need to write this one for rotary type system, d omega f will equal I d lambda minus the torque multiplied by d theta. So here the same, I can calculate also the force for the linear type motion or the torque for the rotation type motion from a partial derivative minus the partial derivative of the field energy with respect to the displacement, x for the force and theta for the torque, in one condition that I should fix what? Lambda, or the function should be described in terms of lambda to fix it. Huh? But remember that this one is mathematically required, not physically required, which means that in order to do the chain rule here, if we still remember that, if I need to differentiate here, we did use the chain rule. Now the chain rule states that if you need to differentiate, you should fix one of the variable, differentiate. So this is a mathematical requirement, not a physically requirement, or not a physical requirement. Now this is the way to calculate the torque or the force using the field energy. What about if I need to use the Coenergy? What about if I need to use the Coenergy in order to calculate the torque or the force? So here, using, for example, the Coenergy. Now remember that omega c plus omega f was equal to what? I lambda, whatever the system is, huh? Linear or nonlinear. Of course, if the system is linear, we are on the safe side. We can we already know how to calculate omega c, and simply we can do the calculation. Now, for general, whatever the system is, linear or nonlinear, the following relation is valid, which means that omega c plus omega f is equal I lambda. So from here, I can calculate omega C, which equal to what? I lambda minus omega F. So if I calculate d omega C, who can calculate d omega C for me? Here I should use what? Chain rule. So this will equal lambda di plus
I lambda
I d lambda minus
d omega
d omega F. But I think we know the value of the omega, d omega F. Yeah? This one.
هي I d lambda by dt minus f dx by dt.
Yeah, which is I d lambda minus f dx if I'm assuming a linear motion. Huh? So let's substitute. If we substitute, then d omega c will equal lambda di plus I d lambda minus I d lambda plus f dx. So this one will eat this one, and we will end up with d omega c is equal lambda di plus f dx. Now the same thing. If I replot the I lambda curve and plot the first curve for, let's assume, x1 position at certain lambda, certain current, I'm having this area. If the position is changing, let's assume to this point, x2, then now I'm having another curve. Then simply this means that the Coenergy now is also a function of what? Omega C is a function of what? Of the
X.
current and x, correct? So if the Coenergy is a function of the current and the x, so I can calculate d omega C by dt, which is equal to what, according to the chain rule? If omega C is a function of the current and x, and I need to differentiate it, then this will equal to partial omega C by partial I when x is constant di plus partial omega C by partial x when the current is constant dx. Yeah, so now if I compare, comparing now, this one is equal to this one, and this one here is equal to this one. So now if I compare, then I can calculate the force, which equal partial omega C by partial x when I is constant. And if I need to calculate the torque, it will equal partial omega C by partial x when the current, partial theta, sorry, the torque is connected to the angular motion. So partial omega C by partial theta when I is constant. And remember, I constant, x constant, this is have nothing to do with the physical system. It's only a mathematical requirement. So here I will write a note for you, keeping I constant, x constant, or lambda constant, have nothing to do with the physical system. It's only mathematical requirement. In order to do the chain rule, I must fix the variable. So it is only a mathematical requirement. Now, if we try to summarize here, we can calculate the torque or the force, or let's make it here like linear time motion. And here, rotation type motion. And here we can say using the field energy omega F or the Coenergy omega C. Now, if I need to calculate the in the linear motion, I will calculate the force. So F will equal minus partial omega F by partial X when lambda is constant. And for the rotation type motion, I need to calculate the torque. So the torque is equal minus partial omega F by partial theta when lambda is constant. If I need to use the Coenergy, then here I will calculate the force, which equal partial omega C by partial X when the current is constant. And here I need to calculate the torque for the rotation using the Coenergy. So partial omega C by partial theta when the current is constant. Which one I'm using, the field energy or the Coenergy? In the end of the day, I should calculate the same expression. Yeah. So someone will ask, which expression to use? Should I use the field energy or should I use the Coenergy? If the two methods.
For linear type, the field energy is the same as the core energy.
Yeah.
And so there is no difference.
Just a minute. For linear magnetic circuit, not linear time motion, there's different.
Oh.
Huh? Now this one is the linear time motion, which means that linear motor, huh? And the magnetic circuit here can be nonlinear. Because if I did not neglect the saturation or the eddy current, in the end of the day, I think all of you know that the BH curve or I lambda curve, huh? I lambda curve or the BH curve, in general, we plot it as this one, huh? And simply here we say that the core entered to saturation. And in general, if we need to design the machine, we design it near the knee here in order to optimize the torque. Yeah. So in general, or in actual life, or the magnetic circuit is nonlinear, by the way, yeah? Even for a linear motion or linear motor. Huh? So here, linear type motion means linear motor, huh? And this is what the rotary type machine. So now which one to use is depend on the simplicity. Sometimes it's more simple to use the field energy. Sometimes it's more simple to use the Coenergy in order to calculate the torque. And for that, I will give example here.
دكتور بس معلش سؤال. باللينير موشن ايش حكيت انه هم مش نفس بعض الاوميجا سي والاوميجا اف؟
No, I didn't. She told me that for linear motion all the time, the magnetic circuit is linear. And I told her that linear time motion does not necessitate that the magnetic circuit is linear. Yeah. So this linear here, linear time motion, stands for linear motor. Not the magnetic circuit is linear. Yes. But if the magnetic circuit is linear, and here I will plot a linear magnetic circuit, then omega F here is equal omega C. But for the nonlinear magnetic circuit, omega F not equal to omega C. This is the magnetic circuit, not the linear motion, rotation time motion. Understood? So don't mix between the motion type and the magnetic circuit type. Yes? Sometimes a linear motor has nonlinear magnetic circuit. And sometimes the rotary type motion, we can assume that the magnetic circuit is what? Is linear. Sometimes we can restrict ourselves to work in the linear magnetic circuit. Yes?
Yes.
Okay. So let's assume that given omega F for single excited system, it was 1/2 Lx I square, and I need you to calculate the force. Find the force. And assume this is one is linear magnetic circuit. Given omega F equals to 1/2 Lx I square, find the force assuming linear magnetic circuit. So let's try to find the force in the two methods, using the field energy and using the Coenergy. Now, if I need to find the force using the field energy, what I should do? Do you remember the force was equal to what due to the field energy? I think I wrote it here.
Minus d omega F على dx.
When
lambda constant.
Lambda constant, okay. So it's a partial minus partial omega F by partial x under one assumption lambda must be constant, yeah. And this condition is mathematically requirement, not physically requirement. Yeah, good. So the first thing, if I need to use this one, omega F must be written as a function of what? Here, omega F is written as a function of lambda and x, yeah?
Yeah.
And here, omega F is written as a function of what? As a function of what? X and what?
Current.
And I. So the first thing, what I should do, I should write omega F. If I need to use this one, if I need to use the field energy, it must be written in terms of lambda and x. So what I can do, I know that lambda is equal Lxi. So I can now substitute I, which equal lambda over L. I can substitute it here, yeah. If I do so, I can find omega F, which will equal 1/2 lambda square over Lx. Now, this one, omega F, is a function of what? Of lambda and x. Now I can do the partial derivative, yes? But I cannot do it here. Yes? So now I can do this one, and I can find the force. If I will differentiate, this will equal to what? Minus here, partial by partial x, and here I'm having lambda square over 2, the constant. I'm assuming lambda is constant. And I will end up, I need to differentiate 1 over Lx, yeah? Yes. Now, if I differentiate this one, this will equal what? Lambda square over 2. And here I'm having partial L, partial X. And here I'm having Lx square, and the minus will eat the minus. Huh? So in the end of the day, I will have lambda square over 2, 1 over Lx square, partial L with respect to partial X. And this is the force. Yes. Now, in general, you know that if I need to write the force, and if we recall the first lecture, the electromechanical energy conversion, it was to write the force or the torque as a function of the machine variable, which is the current and the displacement, not the flux and the displacement. In general, I can measure the current, but it's hard to measure the flux, correct? So now I need to substitute the variable, which is lambda is equal Li. So now the force can be written as I square over 2 Lx square over Lx square partial L by partial X, and simply this will equal 1 over 2 I square partial L by partial X, which is the same expression we did when we discussed the singly excited or the single excited system, correct? How many steps I did need here to calculate the force? The first thing, I need to rearrange the field energy such that it's written as a function of lambda and x. After that, I will evaluate the partial derivative. Then I will substitute lambda in terms of the current in order to have the force as a function in the machine variable, which is the current and the displacement. Yeah. Now, what about if I will use the Coenergy? And I think we assumed that the system is linear magnetic circuit. Yeah. Correct. I think in the question we did assume that linear magnetic circuit. So under this assumption, this means that omega c is given, yeah? Yes or no?
Yeah, it's equal omega f, yeah.
Okay. So now I can say that here, according to the Coenergy, then the force will equal partial omega c by partial x when the current is constant. Correct? And now let's see. Omega c is equal to omega f, yeah, which equal 1 over 2 Lx I square. So this means that omega c is a function of what? Omega c is a function of what?
I and x.
So I can evaluate the partial derivative directly, correct? Yes? I can evaluate it here. So if I evaluate, this will equal to what? 1 over 2 I square partial L by partial x. I'm getting the same result, but simply here in one step, correct? Yes? Here, one step, and I'm getting the result. So this is more easy to use the Coenergy to calculate the force. Yes? Understood? Another example? Let's discuss another example. let a rotational system which has the following relation. I equal lambda minus 2 lambda cosine theta. And I need you to find the torque. Find the torque. Why here I'm saying torque, not force? Because this system is what? Rotational type system. Huh? So I need to find the torque. How I can find the torque now? Here I did not give you the field energy or the Coenergy. I'm giving you a relation between what I and lambda, correct? So from there I can calculate either the field energy or the Coenergy, and from there I can calculate the torque. So who can help me with that? Let's assume that I need to calculate the field energy. I will calculate the torque using the field energy. So omega F equals.
We will use the integration, يعني I integration of I d lambda.
D lambda. So now let's see, this will equal the integration of lambda minus 2 lambda cosine theta r. Let's assume this is theta r. Cosine theta r d lambda. Yep. Now, can you integrate this one? Yeah, this is a cheesecake. Huh? Very simple to integrate. This will equal to 1 minus 2 cosine theta r all multiplied by lambda square over 2. Now this one is a function of what? This one is a function of what?
Theta and lambda.
So this is a function of theta r and lambda. So can I use it directly to calculate the torque? Yes. The requirement is what? The torque is equal minus partial omega f by partial theta r when lambda is constant. Correct? Now, if I do the math, this will equal to what? Who can help me with differentiation? So this will equal to what? This, the constant is 0. Cosine, if I'm using d by dt of the d by
cosine theta r في لمدة تربيع.
So this will equal sine theta r lambda square plus or minus?
لا plus.
Plus. What about this one here?
Yes, okay.
Plus.
Minus.
Now you know that partial cosine theta r by partial theta r is equal to what? Minus sine theta r. Yeah? So minus will eat this minus, and I still have here the minus. Yeah? Good. Yes. Now, if I need to write it in terms of the current, I will substitute instead of lambda with the current. Yeah, I will do it later on. What about if I'm using the Coenergy? The Coenergy. Now, if I'm using the Coenergy, I will calculate omega c. Omega c equal to what according to the area? It will be the integration of lambda di. Yeah. Good. So if we recall I was equal to 1 minus cosine theta r, and here 2 lambda. Yeah. So simply this means that lambda is equal to what? I over 1 minus 2 cosine theta r. In order to do the integration, I will substitute now this one here. So omega c will equal the integration of I di, and this is the constant, 1 minus 2 cosine theta r. So this will equal to what? 1 over 2 I square over 1 minus 2 cosine theta r. Now, if I need to calculate the torque here according to the Coenergy, now let's see before that. This is a function of what?
I theta r.
So I can use the differentiation directly. Huh? I can say that the torque is equal partial omega c by partial theta r when I is constant. Yes? Correct? Now, if I need to do that, 1 I square over 2 is constant. I will leave it out. And this will be, if I need to differentiate, this will be the 1 minus 2 cosine theta r all square. And here I'm having this one here, which will be the minus. Then I have another minus, so it's be a minus 2 sine theta r. So this 2 will eat this one. And if I need to substitute instead of I square 1 minus cosine theta square with lambda, so this is again will equal 2 minus sine theta r lambda square. So if I need to write the torque in terms of the current, this is also T will equal minus sine theta r over 1 minus 2 cosine theta r all square multiplied by I square. This is the torque in terms of the current. And this is to show you that whether you are using the Coenergy or the field energy, you should get the same result. Which one is straightforward? You will use in the end of the day. So my recommendation, if you have the field energy is written in terms of the flux linkage and the displacement, then use the field energy to calculate the torque. But if the field energy is written in terms of the current and the displacement and the system is linear, then automatically you will have the Coenergy. Then you will use the Coenergy because you can evaluate the partial derivative. Do you have any question until here? Do you have any question? No? Okay. So the last example before finishing this lecture. Let's assume that we have electromechanical system. So given and electromechanical system which has two electrical inputs. with the following flux linkage. Lambda 1, which is a function of I1, I2, x is equal to x squared I1 squared plus x I2, and lambda 2, which is a function of I1, I2, and displacement x equal to x squared I2 squared plus x I1. I need you to find omega f, omega c, then an expression for the force. Think about it. So I need you to find omega f, the field energy, omega c, the Coenergy, and an expression of the torque. How I can solve this problem? Here I'm giving you what? Lambda 1 and lambda 2. Huh? I'm giving you lambda 1 and lambda 2. So how I can solve this problem? Let's ask Majid. Majid. Majid.
دكتور مجد.
مجد آسف. مجد. How I can solve this problem, يا مجد? Do you know?
No.
Huh?
لا دكتور.
What about Muhammad? يا محمد.
دكتور.
Do you know how I can solve this problem?
دكتور بقول اليو اف is equal التكامل للمدا 1 في دي اي 1 زائد.
According to Muhammad, he said that omega f is equal the integration of I
lambda 1
d lambda. Okay, so this will equal to what?
بعدين بكتب الاي 1 بدالة اللمدا 1.
Okay. So this will equal the integration of I1 d lambda 1 plus I2 d lambda 2 when I2 equal to 0. Remember the two-stage integration plus the integration of I1 d lambda 1 plus I2 d lambda 2 when I1 is constant. So here I'm doing what? Two-stage integration. I'm doing what? Two-stage integration. So now due to the first stage, I will have this will equal to 0. So I will have I1 d lambda 1 plus the second stage, I will have the I1 capital d lambda 1 plus I2 d lambda 2. Now let's evaluate. Now partial lambda 1 with respect to partial I1 is equal to what? This one. This will equal to what? Partial lambda 1 to respect to I1 is equal to x square I1. Also, I need to evaluate partial lambda 1 with respect to partial I2, and this will equal to what? X. And I need to evaluate partial lambda 2 with respect to partial I2, and this will equal to 2 x square I2. So now omega f will equal I1 partial lambda 1 partial I1 d I1 plus the integration of I1 partial lambda 1 partial I2 d I2 plus I2 partial lambda 2 by partial I2 d I2. So simply now we have all the missing. So here I will substitute this one. Here I will substitute this one. And here I will substitute this one. And I can evaluate. So omega f will equal to the integration of 2 x square I1 square d I1 plus the integration of I1 x d I2 plus the integration of 2 x square I2 square d I2. Now if I do the equation, the integration, then omega f is equal 2 over 3 x square I1 cube plus I1 I2 x plus 2 over 3 x square I2 cube. And this is the field energy. What about the field energy? Can I use the field energy to calculate the torque? Can I use the field energy to calculate the torque? I need to calculate the torque. Huh? First thing here, I found the field energy. Can I calculate the torque directly?
دكتور صاحب تكتبها بالدائرة اللامدا.
Can you write it in terms of lambda? It's difficult, huh? Do you see? This system linear or non-linear? Can I write lambda as L x multiplied by I here? Can I?
لا دكتور لا.
So this is a non-linear magnetic system, is that correct? Which means that omega f is not equal omega c. So it's difficult to use what? The field energy in order to calculate the torque. Yeah. If I'm having the field energy, I need another step, which means that I need to write it in terms of what? X and lambda. And because here the relation between lambda and the current is not straightforward, and here simply I'm having square, so it will be difficult. Huh? So the possible scenario, I should calculate the Coenergy, omega c. Now omega c equal to what?
I lambda minus omega f.
The integration of lambda di, correct? Yeah. Omega c is the integration of lambda di. I think you said that you will use the omega c plus omega f is equal I lambda, correct? And from here you can calculate omega c, which equal I lambda minus omega f, but this will be difficult, by the way. Now, let's calculate omega c, which equal the integration of lambda di. Now, the same thing here, I will do the two-stage integration. So the first one, I will do lambda 1 di1 plus lambda 2 di2 when I2 equal to 0. This is stage number 1. And I will do the integration due to the stage number 2 when I1 is constant. Lambda 1 di1 plus lambda 2 di2 under the assumption that I1 is reaching its final value. So I1 is constant. Now, if I evaluate, if I do the math, this is left for you to evaluate at home. I will find that omega c is equal to 1 over 3 x squared I1 cube plus x I1 I2 plus 2 over 3 x I2 squared. Now I can use this one to calculate the torque. So the torque is equal partial omega c by partial x when I is constant. Now this, if I evaluate, will equal 2 over 3 x I1 cube plus I1 I2 plus 2 over 3 I2 squared. Okay, I think here I'm having 2. So this will be the, this is my mistake here, I'm having 1. Okay. So 1 over 3 x squared. This is the Coenergy. 1 over 3 x squared I1 cube. And here I think it will be cube also. And plus x I1 I2 plus 1 over 3 x squared I2 cube. Now I can calculate the torque, and it will be 2 over 3 x I1 cube plus I1 I2 because I'm differentiating with respect to x plus 2 over 3, and here I'm having the x. Here I'm missing the x. Yeah. So it's left for you to double check those two formulas, the Coenergy and the field energy. And simply because the omega c is not equal to omega f, then the system is nonlinear, or the magnetic circuit is nonlinear. So nonlinear magnetic circuit. Do you have any question?